Hello, let's solve network recovery pathways. I will assume that you have read the problem statement already. And so they ask us to, among all the valid paths that can reach n-1 in less than k cost, which one has the maximum score, and the score being defined as the minimum cost along that path. Right, and here, for example, if we compare the path 0, 1, 4, which has a total cost of 12, and 0 to 4, which also has a total cost of 12, the best path, according to the problem statement, is 0 to 4, because the minimum cost is 6. For 0, 1, 4, the minimum cost is 5. We could try to look at all of the valid paths, and then for each of them we could compute the minimum edge cost along those paths, but that would take too long because there could be many paths, and computing the minimum along one path is already big of n the number of vertices as well, so that would take way too long considering we have at most 50,000 nodes and 100,000 edges. What we can do instead is try and use binary search. So we can ask ourselves, is there a way to arrive to node n-1, so 4 here, using only edges that have at least a cost of 10? Here it's not possible. And then we can ask the question, can I arrive to n-1 using only edges that have cost 5? And then the answer would be yes. And so we would ask, is it possible with 7? The answer would be no. And we would ask, is it possible with 6? And the answer would be yes. And in that way, we don't iterate through all the paths. We just do one shortest paths algorithm log times, because we're doing binary search. So we're doing log times a shortest path algorithm. So that would be the cost of a shortest path algorithm times log n complexity. And to do shortest path algorithm, we could just use Dijkstra algorithm, because all of the edges, have positive weights, but that would be a total complexity of n log square, which is, I guess, not great, because since we have a directed acyclic graph, we can do better. We can just use the fact that there is a topological order in this graph to do the shortest path in linear time instead of log linear time. And so to solve this exercise, you need to be familiar with how to do shortest path when there is a topological order. So very briefly, for those who may have forgotten, if I'm considering a graph like this, with edges that have weight, and I use a standard BFS algorithm, I would first say that distance of 0 is 0. I would say then distance of 1 is 1, and distance of 3 is 50. Right, this is a BFS algorithm. And then I would say distance of 2 is 2, and then distance of 4 is 52. But then I would come back to 3, and I would say distance of 3, because I'm following a BFS ordering. I would say, well, now actually distance of 3 is 3. And that means that all of the work that I've done post 3, I have to do it again, because I've updated the minimum distance to reach 3. So the minimum distance to reach 4 is now invalid. Right? So that's why BFS typically doesn't work when there's edge weights. And we can solve this when we have a directly directed acyclic graph, which is the case here, because we can say there is a topological ordering. Here, for example, that would be 0, 1, 2, 3, before. By definition, it means that when a topological ordering is defined as if I'm here, none of the nodes that come after have an edge that goes to me. All right, and what is that called? That means that if I do the same algorithm, but I follow, instead of following a BFS ordering, I follow this topological ordering. When I arrive at a node, I'm sure that the distance I have is the minimum one, because literally no one has an edge going to this node, so I can never update this distance ever again. So I'm sure it's the minimum distance. Right? So this is why when we have directed acyclic graph, we can have very cheap shortest path, and we don't need to use Dijkstra's or any other complicated algorithms. And so if we come back to our problem, we'll basically do a binary search, and we'll ask the question, is it possible to go to n-1 only using edges with a certain cost? If that's possible, then we know that the maximum path score is at least this value. And if it's not possible, we know that maximum path score cannot be larger than this value. And for each of these binary search iterations, we'll just do a shortest path algorithm using this topological ordering so that it's linear time. And the graph that we'll consider will be the graph where we only consider edges that have a cost at least equal to this value we're binary searching. This clearly will be clearer when we do the code, but that's the idea. So let's code this up. The first thing we have to do is to get our adjacency lists. So we'll just initialize a list of dictionaries. And so graph u v equals w means there is an edge from u to v with weights w. And that's a directed graph. So when we have an edge from u to v, it doesn't mean we have an edge from v to u. So for u, v, w in edges, we can say graph u, v equals w, but we can actually do even better. If u is offline or v is offline, then those are nodes we're not allowed to take, so there's no need to add them in the graph, and it'll make our algorithm slightly faster. So let's just do if online u and online v, we add the edge. Now that we have our graph, we need to find this topological ordering. Here the topological ordering was 0, 1, 2, 3, 4, and so we need to find it, and the way to find it is just to use Kahn's algorithm. And so we, again, I'll just assume you're familiar with it. We initialize a list that tells us how many edges go to that node, and every time we add an edge to our adjacency list, we can just do in degrees of v plus equal 1. Then we have our q, dec integers. We add all of the nodes that have 0 incoming edges, so they'll obviously be at the start of a topological ordering. For node in range length of online, if in degrees of node equals 0, 0, and if that node is online, I guess lead q dot append node. Right, this is a q, so we'll just append left and pop right. And then we'll initialize topological or list of topological order list whilst there are things in the queue, we pop from the right, because it's a queue, we append left, we pop from the right. We add it to the topological order object, and we consider all the neighbors in graph nodes. We do in degrees of that neighbor minus equal 1, because now we don't consider this neighbor anymore. And if neighbor doesn't have any incoming degrees, then we can add it to the queue. If in degrees neighbor 0, queue that open left neighbor. Now that we have our topological order, we can just do the binary search. So we initialize low, which will be 0. Actually, low will be -1. The reason for that is because if there is no valid path, we want to return -1, but there also could be a valid path for which the maximum path score would be 0, because edges can have cost 0. So maybe if k is 0 and all the edges are 0, well, the maximum score we can get is obviously 0. So 0 and -1 are not the same, so we'll have a -1. High is k, because for a valid path to exist, the total recovery cost of all edges cannot exceed k. So obviously the minimum edge cost cannot exceed k either, because all the weights are positive. While low is smaller than high, mid will be low plus high plus 1 divided by 2. And we'll do if self dot can reach end with score of mid, and we'll give it the graph, we'll give it the topological order, we'll give it mid, and we'll give it k. Then we'll have low equal mid, and otherwise we'll have high equals mid -1. The reason why we give it the topological order to this function is because our algorithm needs the topological ordering, and we don't want to calculate the topological ordering every time. It's always going to be the same. So we calculate it before and we just give it. Obviously need the graph. Mid is just to filter out the edges that have a cost below mid, because we're checking if we can have a score of mid, and to have a score of mid we can only use edges with a weight of mid, and we pass it k because we want a valid path, and for the path to be valid we need to reach the end with a total accumulated cost that is less than k. And then we can just return low, and then let's define a function, graph list of dictionaries of ints, topological order is a list of integers, mid is an integer, and k is an integer. And this returns a boolean. And so we'll just use the very standard algorithm. We have our variable min distances. Initially we'll just put very high numbers in it, except for the starting points, and then we iterate through all the nodes in the topological ordering. Obviously, if node is equal to n-1, we'll just return true if we can reach n-1 less than k accumulated cost, and false otherwise. So we can just return this, and doesn't exist, sorry. If min distances of node is above k, we don't even need to update the neighbors of node, because we know that this path is doomed anyway. It's already too big. So that's a slight micro optimization, I'd say. And otherwise, we can just iterate through the neighbors for neighbor graph nodes. But we only want to, we said we wanted to filter out the neighbors if the weight of the edge was smaller than mid. So if graph node neighbor is bigger than mid, then we can do something. And something is just to update mid distances of neighbor with what it had, and the new distance, which is min distances of node plus that distance, graph node neighbor. So that seems pretty much correct to me, and we should never arrive here, because in our topological ordering we will have the last node, so we should return before we exit the loop. So we should never arrive here. And I think that's pretty much it. Maybe there's a few typos. Let's verify. Okay, so the test case is provided by Leetcode pass. You can just copy paste this and submit. And there's an error, and I think the problems comes from here, because there's probably duplicates, so several edges going from the same U to the same V. And if that's the case, we shouldn't increase, because we've already increased it in the new edge. So yeah, instead of a dictionary of int to int, it should be dictionary of int to list of ints. And that would be a default dict of a list, and then we would have something like this. Means there's an edge from U to V with weight W1 and another one with weight W2, because otherwise we're just erasing the edge, which is not good. So here we'll just do dot append W, and in degrees V plus equal 1. And so what does that change? Doesn't change anything here. Actually, for neighbor in graph node, we'll just remove the length of graph node, neighbor. Need to change this here. And in the shortest path, we'll do for neighbor in graph node, and we'll do something like for edge in graph node neighbor. If the edge is bigger than mid, then we can try and update it like this. And that should be correct now. Okay, the sample test cases pass, and the submission works. And yeah, that's it.